Inside the drone revolution, how drones are manufactured and why they are changing modern warfare over the last 2 decades. A quiet technological revolution has taken place in the skies. Small unmanned aircraft that once appeared mainly in research laboratories or hobby shops have now become central tools in modern security and defense strategies. These machines are known as drones or unmanned aerial vehicles. They are aircraft that fly without a human pilot inside the cockpit. Instead, they are guided by computers, sensors, and operators on the ground. In the past, only a few powerful countries could dominate the skies with advanced fighter aircraft and strategic bombers. Air power required enormous investments in engineering, pilot training, maintenance systems, and specialized bases. Today, the situation is changing rapidly. The rise of drones has made aerial technology more accessible and more flexible. Understanding how drones are manufactured and how they operate helps explain why they are transforming modern military thinking. The story of drone technology begins with the development of lightweight electronics. Modern drones are made possible by advances in microprocessors, sensors, batteries, and communication systems. These technologies allow small aircraft to stabilize themselves automatically, navigate long distances, and send information back to operators in real time. At the heart of every drone is the airframe. The airframe is the physical body or skeleton of the aircraft. It holds all the other components together and determines how the drone moves through the air. Engineers design airframes using aerodynamic principles so that the aircraft can fly efficiently and remain stable even in changing wind conditions. Many modern drones use lightweight materials such as carbon fiber or advanced polymers. Carbon fiber is extremely strong while remaining very light. This combination allows drones to carry cameras, sensors, or other equipment without becoming too heavy to fly. The shape of the airframe also determines the type of drone. Some drones resemble small airplanes with fixed wings that allow them to glide long distances. Others are multi-rotor drones that use several propellers to hover and maneuver precisely in small spaces. Another essential part of a drone is its propulsion system. Propulsion provides the force that lifts the aircraft into the air and allows it to move forward or change direction. In many small drones, the propulsion system consists of electric motors connected to propellers. These motors spin at very high speeds and generate the lift needed for flight. Most modern drones use brushless electric motors. Brushless motors are efficient, durable, and capable of operating for long periods without significant wear. They are controlled electronically, which allows the drone's onboard computer to adjust their speed continuously in order to maintain balance and respond to commands. Powering these motors requires a reliable energy source. That energy usually comes from rechargeable batteries. Lithium polymer batteries are commonly used in drones because they provide a high energy output while remaining relatively lightweight. Battery technology has improved significantly over the years, allowing drones to stay in the air longer than earlier models. Flight endurance, which is the amount of time a drone can remain airborne, depends largely on battery capacity and energy efficiency. Engineers constantly work to improve battery performance because longer endurance allows drones to travel greater distances and perform longer missions. While the airframe, motors, and batteries form the physical foundation of the drone, the true intelligence of the aircraft lies in its flight control system. The flight controller is essentially a small computer located inside the drone. It acts as the brain of the entire system. The flight controller receives information from various sensors installed throughout the aircraft. These sensors include gyroscopes and accelerometers that measure the drone's orientation and movement. By analyzing this data, the flight controller can automatically adjust the speed of each motor to keep the drone stable. This process happens many times every second. Even when the drone appears to be hovering perfectly still, the flight controller is constantly making tiny adjustments to maintain balance. Without this automated stabilization system, controlling a drone would be extremely difficult. Navigation is another important capability built into modern drones. Many drones rely on satellite navigation systems to determine their position on the Earth's surface. These systems allow the drone to know exactly where it is and where it needs to go. Using satellite navigation, operators can program drones to follow predetermined routes. The drone can travel from one waypoint to another while maintaining altitude and direction automatically. This ability allows drones to conduct long surveillance flights or mapping missions without constant manual control. Communication systems connect the drone with its operator. Radio transmitters and receivers allow commands to travel from the ground controller to the aircraft. At the same time, video and data collected by the drone can be transmitted back to the operator in real time. This communication link is extremely important. It allows operators to monitor the drone's flight path, adjust its mission, and observe what the drone's cameras are seeing. Advances in digital communication have made it possible for drones to transmit high resolution video over significant distances. Cameras and sensors are often among the most valuable parts of a drone. High definition cameras mounted on stabilized gimbals allow drones to capture clear images even while the aircraft is moving. These cameras are widely used for photography, filmmaking, environmental monitoring, agriculture, and infrastructure inspection. In security and defense applications, cameras and sensors allow drones to observe terrain, track movements, and gather information that might otherwise be difficult to obtain. Infrared sensors can detect heat signatures, making it possible to observe activity even at night or in low visibility conditions. All of these hardware components are coordinated by sophisticated software systems. Drone software controls navigation, stabilization, communication, and mission planning. Some drones can be programmed with flight plans that guide them through complex routes automatically. Software also manages safety features. Many drones include automatic return systems that guide the aircraft back to its starting point. If communication with the operator is lost or if the battery level becomes too low. Another emerging area in drone technology is the use of artificial intelligence. AI algorithms can analyze images captured by drone cameras and identify objects or patterns. This capability can be useful in applications such as disaster response, wildlife monitoring, and environmental protection. Manufacturing drones involves integrating all these components into a reliable system. The production process often begins with computer aided design. Engineers design the airframe and electronic layout using specialized software that allows them to test different configurations before building physical prototypes. Once the design is finalized, manufacturers produce the airframe components using precision machining or advanced molding techniques. Electronic circuit boards are assembled to house the flight controller and communication systems. Motors, sensors, batteries, and wiring are installed carefully to ensure proper balance and performance. After assembly, each drone undergoes testing. Engineers perform ground tests to verify that the electronics function correctly and that the motors respond properly to control signals. Test flights are conducted to evaluate stability, navigation accuracy, and communication reliability. Quality control is critical because even small mechanical or electronic problems can affect flight performance. Manufacturers inspect each component carefully to ensure that the drone meets safety and performance standards. The global drone industry has grown rapidly as these technologies have become more widely available. Companies around the world now produce drones for commercial, industrial, and research purposes. The same basic technologies that allow photographers to capture aerial images also support scientific research and environmental monitoring. In recent years, drones have also gained attention because of their role in modern conflicts. Military planners recognize that drones can perform tasks that once required much larger and more expensive aircraft. They can gather information from the air without risking the life of a pilot. Because drones are smaller and less expensive than traditional aircraft, they can also be produced in larger numbers. This has led many analysts to study how drone technology might influence future military strategies. Conflicts involving countries such as Ukraine and Russia have demonstrated how widely drones are being used for surveillance and battlefield awareness. Similar technologies are also being studied and developed by many other nations, including Iran. These developments have encouraged governments to invest in new methods for detecting and countering unmanned aircraft. Radar systems are being adapted to identify small flying objects, and electronic systems are being designed to disrupt communication links between drones and their operators. At the same time, engineers continue to improve drone technology itself. New battery systems promise longer flight times. More powerful processors allow drones to analyze information quickly while still in the air. Advances in artificial intelligence may allow future drones to navigate complex environments with minimal human guidance. The growth of drone technology illustrates how innovations in electronics and software can reshape entire industries. What began as experimental aircraft has become a global technological movement influencing transportation, agriculture, filmmaking, scientific research, and security. As these machines continue to evolve, they will likely play an even greater role in the skies above us. Their development reflects the broader trend of automation and intelligent systems transforming the way humans interact with technology. Understanding how drones are manufactured and how they operate provides insight into one of the most important technological shifts of our time. From lightweight materials and high efficiency motors to advanced sensors and powerful software, drones represent a remarkable combination of engineering disciplines working together. The drone revolution is still unfolding, and its influence on both civilian industries and security strategies will continue to grow in the years ahead.